All right, so we're going to pick up where we left off last time talking about these Grignard reactions. These are ways to prepare alcohols where in the process we create a new carbon-carbon bond, and they use these weird organometallic compounds, these Grignard reagents. All right, so everybody take a second, see if you can't give me our product for this Grignard reaction.
In the video that I watched since I was gone, like I noticed.
Oh, the coloring?
Yeah. Sometimes I can put a little dot.
Yeah, for sure.
It's going to be on the opposite side.
Keep track of what's what. It's very helpful. All right, so one of the most important things to remember about these Grignard reactions is that we're creating a new carbon-carbon bond. So where are those new carbons going to be, or rather, which two carbons are we going to put our new bond between? It's going to be the carbonyl carbon, the one at the base of that carbon-oxygen double bond, and our carbon in our organometallic compound that is attached to the magnesium. In this case, there's only the one. But this is where my new bond is going to be in my products. So I'm going to start by redrawing my ketone here. I got these 1, 2, 3, 4, 5, 6 carbons in a ring. All right, this one at the top is my carbonyl carbon, or at least it used to be. And so when I draw my new carbon-carbon bond on the other side, it has to be that red carbon. All right, and remember the magnesium and the bromine are not going to appear anywhere in your product. They get chopped off. I am missing one thing though, which is my ketone oxygen here. All right, that doesn't go away, but it does go from being a carbon-oxygen double bond to just a carbon-oxygen single bond. All right, so our Grignard reaction, we take an aldehyde or a ketone and treat it with this Grignard reagent, this organometallic compound. We get an alcohol product that has a new carbon-carbon bond. All right, and remember we said the best way we can check our work here is to count carbons. I got these 1, 2, 3, 4, 5, 6 carbons from my ketone, plus just one more from that Grignard. Cool. All right, what's up?
Is there a reason why you can't do it like that?
So the new bond is not going to be with the oxygen. It's going to be a carbon-carbon bond, always a new carbon-carbon bond, and that's a new oxygen-carbon bond, right? So we just always have to do a carbon-carbon bond, and it's going to be that carbonyl carbon, the one at the base of the oxygen, that's going to have the new bond in your ketone. All right, so now let's say that we're given an alcohol. Let's see if we can't work backwards here. All right, what would my Grignard be? And what would my aldehyde or ketone be? My carbonyl compound, in order to create this alcohol here. All right, so importantly, what we know right off the bat, just by looking at this alcohol, is that this carbon right here, the one at the base of that OH group, has to be my carbonyl carbon, right? It has to have a carbon-oxygen double bond on this side. All right, but these reactions also create new carbon-carbon bonds. So one of these two, and because this molecule's symmetric, it doesn't matter which one I pick. I'm just going to select the one on the right here. In my reaction here, this is my new carbon-carbon bond. Okay? I could have picked the one on the other side. We'll do an example here where it's different, but the bottom line is in this reaction, I know two things. I know that I have to start with a carbonyl-containing compound. I have to have a carbon-oxygen double bond. And I have to create a new carbon-carbon bond, right? So when we're working backwards, the first thing we can do is say, all right, well this, the one that's bound to the oxygen, just like we saw up here, that has to be my carbonyl carbon. So that's my carbon-oxygen double bond to that blue carbon. Okay. If that's my new carbon-carbon bond, then I still have one more over here. And my Grignard has to have that red carbon. Boom. Okay, so based on analogy of what we just saw here, everybody take a minute and see if you can't tell me how we could make this alcohol right here using this Grignard process. All right, so again, what I know for sure is that this carbon right here that is bound to that oxygen, that has to be my carbonyl carbon. So on my reactant side, I know I got a carbon-oxygen double bond. That blue carbon has to be that carbonyl carbon. This reaction also has to create a new carbon-carbon bond between that carbonyl carbon and its next door neighbor. So this thing here is new, which means that on the other side, this must have been the carbon attached to my magnesium, my Grignard. All right, so that means that these three, 1, 2, 3, are going to have to belong to that, in this case, it's an aldehyde. And I got my 1, 2 carbons that were in my Grignard. All right, where the one that was bound to that magnesium is the one on the other side of my new carbon-carbon bond, right? We're effectively at this new bond, we're kind of chopping it into these two chunks. The one that has that oxygen, that has to be my carbonyl carbon, so that's going to be my aldehyde fragment. And the other half is going to be my Grignard. All right, so up until now we've been using these symmetric alcohols, so it didn't matter which side of that carbon-oxygen bond you chopped on. But what if we had something like this? Now let's just use an asymmetric alcohol, like 2-butanol. All right, so I know for sure this has to be that carbonyl carbon, right? Because it has that oxygen bound to it. But there's two ways that I could chop this molecule. I could say, all right, my new carbon-carbon bond is over here on the right. Nope, that's the left. Or I can say my new carbon-carbon bond is over here on the right. And depending on which one of these is my new bond, I would use a different set of carbonyl compound, my aldehyde or ketone, and my Grignard. So everybody, take this top one here. See if you can't, based on what we've done up until this point, tell me what would your aldehyde be and what would your Grignard reagent be? All right, so if this is my new bond, if I'm going to create my reactant side here, then I'm going to chop it at this bond. Which side is going to be my Grignard, the left or the right? The right, because this side over here has that oxygen, so that has to be my aldehyde. Could be a ketone, but in this case it's an aldehyde. All right, and again, I know that what was bound to the oxygen on the left has to be bound to the oxygen on the right. So in this case, I just have that one carbon Grignard. I'm being lazy with my lone pairs here. Okay. And if I said instead it was the other side, now I'm going to chop at this bond. And so now which side is going to be my Grignard, the left or the right? Which side's going to be my Grignard, left or right? No, wait, left. Okay, Grignard would have to be the one that doesn't have the oxygen on it. The one with the oxygen has to be my aldehyde or ketone. So my Grignard in this case is going to be on the other side. Now I'm going to need to use this 2-carbon Grignard. Okay, and again, that carbon that was bound to the oxygen on the left has to be bound to the oxygen on the right. So this carbon must be my red carbon on my product side here. Okay, so we took the same alcohol and we said that we had these two different ways to make it, right? So which one are we going to use? Which one's more preferable? There is like a billion cases in organic chemistry where one of these would be better than the other, but with Grignards, we luck out. There's really just no restriction on what your Grignard could be, what your aldehyde or ketone would be. Either of these reactions would be just as perfectly efficient as the other one. So in this case, we get to luck out and we just pick one and roll with it. All right, so it wouldn't matter which one of these methods you choose to make your alcohol, as long as you correctly formed your aldehyde and your Grignard pair, either one of these would work. Okay, so if there's more than one option, you just got to pick one and roll with it. Okay, so then let's do one more here just for the sake of practice. bonus points if you can give me both. All right, so what's true in both of these, regardless of which sort of set I use, is that that carbon that is bound to that oxygen, that has to be my carbonyl carbon. It has to have that carbon-oxygen double bond. So that's going to be the case in both of these. The difference is going to be which side I decide to chop on. I can either chop over here on the left-hand side and say that this was my new bond that was created. So that means that this was my Grignard carbon. Or I can go to the other side and say that this was my new bond that was created, which means that this has to be my Grignard carbon. Right? So if I'm going to chop at this bond here, that means that this fragment was my aldehyde or ketone. In this case, it's an aldehyde. And that 2 carbon had to have been my Grignard. All right, and again, just to kind of keep my coloring consistent here, it's the carbon bound to the magnesium. That's my red carbon over here. And my carbonyl carbon is that blue carbon. All right, so if we decided to chop this on the left-hand side, this would be our combination of substrate and reagent that we would use. All right, if I do it on the other side, hiya, chop. Now this on the left is my aldehyde fragment. And my Grignard, I guess let me just draw it the same to be consistent. Right, this thing here with my red carbon, that has to be the one that was bound to that magnesium. And again, blue being that carbonyl carbon on both sides. And again, either one of these would be perfectly acceptable full point answers. All right, there's no preference of one method over the other, as long as you give me the correct combination. What's up?
So, does it matter where you put the magnesium? Like if it's on the left or the right side?
So in Portland, so for the top example, no, because this is just 2 carbons in a straight chain. So if you took this thing and, for example, just kind of flipped it over, that's the same thing, okay? For the second example, it's really important that it's on that middle carbon. If you instead tried to pick this thing up and move it over here to the end, well, you wouldn't get this product at the end. You would get your new bond between this carbon and the blue carbon, right? So the magnesium has to be bound to the one where you have that new bond. So I colored it red in this side to show that that's the carbon with my new bond. That has to be where the magnesium is on your substrate, or reagent, I guess, in this case. What's up?
I think he was referring to like on that same middle carbon, but maybe just on the other, like the other leg sticking out on the right side.
This would be perfectly equivalent.
Yeah.
That's kind of what you mean, because it's still bound to that middle carbon. Putting it on the end, though, changes the structure altogether. Yeah. So no, whether it's on the left or the right, as long as it's bound, look, you count these carbons, 1, 2, 3, it better be on carbon 2 and not on carbon 1 or 3 is the bottom line. Cool. All right. So Grignards, very important topic in organic chemistry because, again, they just work so frickin' well, and we really don't have a ton of methods for creating new carbon-carbon bonds. Okay? Another important reaction category of alcohols is what's called oxidation and reduction reactions. All right, so you might remember redox was a topic that you discussed in general chemistry, and you kind of had this pain in the butt method of going in and assigning oxidation numbers to things and figuring out what its oxidation number was on the left and the right, and you could compare them and say what was being oxidized and reduced, and it's kind of like one of everybody's least favorite topics in general chemistry, okay? Now, the good news is, in an organic chemistry, again, we are dealing with such a small subset of elements on the periodic table, we kind of don't have to do the big pain in the butt process. We can simplify things down. When we're talking about oxidation in organic chemistry, we are simply talking about creating more carbon-oxygen bonds. All right, and when we're talking about reduction in organic chemistry, again, we can kind of simplify things down here. We're talking about creating more carbon-hydrogen bonds. So if we take, let's say, we had similar classification of alcohols just like we did our alkyl halides. We're going to take a primary alcohol. A primary alcohol is one in which your hydroxyl group is bound to a carbon with only one other carbon neighbor. Right? This is a primary carbon because it's got only that one other neighbor. If we take an alcohol and we oxidize it, which we're just going to put this little O for right now. Let's just write oxidize. We will now create a new carbon-oxygen bond. So this alcohol group here, my carbon-oxygen single bond, becomes a carbon-oxygen double bond. All right, so what new functional group have we just created by oxidizing that alcohol? So it's a carbonyl, but remember we got these two compounds that are very similar, aldehydes and ketones. Which one is this?
Aldehyde.
So this one's an aldehyde because it's on the very end of the molecule. But aldehydes can actually be further oxidized. We can add even one more carbon-oxygen bond onto there. Ooh. Okay, and this is a functional group we haven't spent much time talking about. It's actually like one of the last ones that we introduced in the course. Does anybody remember what these ones are called?
Carboxylic acid.
It is a carboxylic acid. So primary alcohols can be oxidized to aldehydes, and aldehydes can be further oxidized to carboxylic acids, right? And again, we're not doing that pain in the butt counting oxidation number business. All we're doing is seeing that in each one of these steps, we're creating a new carbon-oxygen bond.
It would have to go to the first step to get to the second, right? Or would we just?
We'll talk about that. Some things go from the first to the second. Some things just plow right through to the end, all right? But we'll talk about that here in a bit. If we go in the other direction, now I'm not creating any carbon-oxygen bonds, but rather new carbon-hydrogen bonds. So if we go in the opposite direction, these are our reduction reactions. So so a primary alcohol can be oxidized to an aldehyde, and an aldehyde can be reduced back to a primary alcohol, right? These are like inverse of one another. All right, now a secondary alcohol. That means that that hydroxyl group is bound to a secondary carbon. All right, this is a secondary carbon because it's got 2 carbon neighbors. All right, based on analogy of what we just did, take a second and see if you can't predict what this is going to be oxidized to. All right, so again, I'm going to turn that carbon-oxygen single bond into a carbon-oxygen double bond. In this case, from a secondary alcohol, I don't create an aldehyde, but now that carbonyl group is in the middle of a molecule. So this is a ketone. All right, but if I tried to play this game again, there's no way to add another carbon-oxygen bond, at least without breaking one of the carbon-carbon bonds. If we look, this carbon in the middle here, it's already got its full octet. There are no more hydrogens on there. And oxidation reactions won't break carbon-carbon bonds. So in this case, we cannot further oxidize this ketone anymore. It's stuck at that step. So unlike primary alcohols, which we can oxidize to aldehydes, but then aldehydes being on the end have an additional hydrogen we can replace with an oxygen, with ketones we only got that one step. All right, and like we said before, the inverse of this oxidation reaction would be a reduction reaction. You can reduce a ketone to a secondary alcohol. All right, and then lastly, we can have a tertiary alcohol. That would be if we had our hydroxyl group bound to, a tertiary carbon. Okay. Let's go ahead and oxidize this and create a carbon-oxygen double bond from our carbon-oxygen single bond. And I hope everybody's organic chemistry brain just exploded when I did that. All right, because what is incredibly wrong with that product that I have there?
5 bonds.
I got 5 bonds on that carbon, right? That is absolutely never going to occur here. So you can't oxidize. Same sort of argument that we were saying before about our ketones not being able to be oxidized. I just don't have anything that I can replace with a carbon-oxygen double bond. So tertiary alcohols are stuck. They cannot be oxidized. Okay? Cool, so we have these primary alcohols that we can oxidize to aldehydes, and then aldehydes can be oxidized to carboxylic acids. For secondary alcohols, they can be oxidized to ketones, but then we're stuck. We can't oxidize a ketone any further. And then from tertiary alcohols, we're kind of stuck right off the bat. They can't be oxidized at all. Okay? Cool, so we just said oxidation and reduction at this point. All right, let's take these primary alcohols. And what we're going to see is we're going to take a look at some specific oxidizing agents here. But we're going to see that the world of oxidizing agents is divided up into 2 categories, strong and weak. A strong oxidizer is one that will completely oxidize a carbon to the max extent. So it's going to oxidize that primary alcohol all the way to a carboxylic acid. No way to stop it at that aldehyde step. Similarly, if instead you did start with an aldehyde and you used a strong oxidizer, it would oxidize it all the way to that carboxylic acid. All right, so strong oxidizers, there's no way to get that aldehyde product. It's just going to blow right through that and get a fully oxidized carbon, a carboxylic acid. All right, but what if we really wanted to create an aldehyde? Well, then instead of using a strong oxidizer, we're going to use what's called a weak oxidizer. All right, a weak oxidizer can oxidize a primary alcohol to an aldehyde, and then it's stuck. All right. So if we start with our primary alcohol, depending on what type of oxidation agent we treat it with, we're going to get a different product. If we use a weak oxidizer, it'll just do that one oxidation step and then stop there. If we use our strong oxidizer, it's just going to completely oxidize that carbon to a carboxylic acid. So then let's look at our secondary alcohol. Cool. go. So a secondary alcohol, we kind of don't have the same concerns that we did with a primary alcohol because there's only one oxidation step. And so it turns out if you used a strong oxidizing agent, well then yes, you will definitely oxidize that to a ketone. But if you used a weak oxidizer, well, that can oxidize to that carbonyl group as well. So you get the exact same product. So the secondary alcohol, doesn't matter what you use. Doesn't matter what type of oxidation agent you use, you'll always get the same ketone product. I will tell you, practically speaking, you're probably going to use your strong oxidizing agents just because they tend to be a little bit cheaper than your weak oxidizing agents. And the lab is really just a business, right? You're trying to save money where you can. For our pencil and paper purposes, doesn't matter what you choose. All right, so let's talk about these these oxidation agents. All right, our strong oxidizer is what's called sodium dichromate. Okay, you usually have that in this acidic mixture here with some sulfuric acid. All right, but it's really the chromium here that will stand out or jumps out to me because chromium is a metal that is very often associated with these oxidation processes. We're just going to talk about one oxidation agent, this sodium dichromate. There are a few different ones out there, but chromium is a common feature in a lot of these strong oxidizers. All right, so chromium equals oxidation. All right. Our weak oxidizers. There's going to be two that we're going to talk about. One of them is in our textbook and is in every organic chemistry textbook, and that is what's called PCC. I don't remember what it stands for, but I remember one of the C's is a chromium. It's kind of this fancy compound that incorporates a chromium but dopes it a little bit so it's not quite as strong. The problem is that it is terrible for the environment. All right, so there's been a big push to get away from these organic chemistry reagents that work really great but are terrible for the environment. There's been a big push to kind of swap them out for what are called green chemistry substitutes. And one of the ones that has become very popular in recent times is what's called DMP. So we're going to learn both of them here. Again, one of them is in our textbook. The other one is one that you'll more commonly see in the wild now. Both are these three-letter acronyms here. Okay, but these are both our weak oxidizing agents. All right, so let's just illustrate the difference here. We're going to take a big complicated molecule with a bunch of hydroxyl groups. All right, and we're going to use this particular example because one of these is a primary alcohol, the other one is a secondary alcohol, and the other one's a tertiary alcohol, all within this same molecule. All right, so let's hit this thing first with our weak oxidizing agent DMP, and then we're going to take that same substrate and use our strong oxidizing agent sodium dichromate. And I want everybody to take a second and tell me what the product of these two reactions would be here, starting with that same reagent, that same substrate rather. All right, so starting out with my substrate here, I'm just going to copy and paste it down. For my weak, and I guess that's the most important step here, right, is we recognize that DMP is our weak oxidizer, whereas that sodium dichromate is our strong oxidizer. So for our weak oxidizer, we're going to take this primary alcohol and we're going to oxidize it just that one step to an aldehyde. What about my secondary alcohol? Does that get oxidized? Yes, so I'm going to take that, add that new carbon-oxygen bond. And then my tertiary alcohol, I'm going to oxidize that. No, because those already have full octet, already has 3 carbon-carbon bonds. Can't create any more carbon-oxygen bonds. Now we're going to take our strong oxidizer. Same idea. Take that same substrate. For a strong oxidizer, what am I going to convert that alcohol into, that primary alcohol into? I'm going to need a fully oxidized carboxylic acid. My secondary alcohol, I can't make a carboxylic acid. I got carbons on either side, but I can oxidize it that one step to a ketone. All right, and even with a strong oxidizer, you still can't oxidize a tertiary alcohol, right? So what you'll notice is the big difference here is what happens with that primary alcohol group. Let's see if I can't color this a little bit easier. All right. For our weak oxidizer, we get an aldehyde, but for our strong oxidizer, it converts it into a carboxylic acid. And that's the big difference, because if we look at our secondary alcohol, this can indeed be oxidized, but regardless of whether I use my weak or my strong oxidizer, I'm still just going to get that ketone. And then my tertiary alcohol just doesn't get touched at all, can't be oxidized at all. All right, so again, the big difference here is what happens on that primary carbon. All right, that primary alcohol group. Cool. All right, so that's our oxidizing agents. What about our reducing agents? All right, your reducing agents are, we're going to learn two different ones here. They all got the same common feature. They're classified as what are called hydrides. And we're not going to talk too much about this other than to say that a hydride is when you have a nucleophilic hydrogen. All right, and I know everybody's all like, what? Hydrogen's a nucleophile. Hydrogen's never a nucleophile, right? Nucleophiles are electron rich. We don't associate hydrogens with being electron rich. Hydrogen's ions are protons. They're positively charged, all right? So that's the weird thing about these hydrides here, is they're these compounds where hydrogen has a ton of electron density, which is just kind of weird for a hydrogen atom. All right, so the two that we're going to talk about are rather that you need to be able to sight recognize, are lithium aluminum hydride and sodium borohydride. All right, and at least for our purposes in this point in our course, there is no difference between these two. Either ones will work just as well in reducing an aldehyde or ketone to an alcohol. All right. What you'll notice is they both have this metal. In lithium aluminum hydride, it's the aluminum. In sodium borohydride, it's the boron that's attached to that hydrogen. So hydrogen's actually the more electronegative species, taking that electron density, again making it a nucleophile. Okay. So let's just do an example here. If we take for example, this ketone, and we treat it with our hydride, lithium aluminum hydride. Everybody take a second and tell me what our product should be of this reaction here. So my ketone will get reduced to a secondary alcohol. All right, and again, remember we called these reduction reactions. And I said that for a reduction reaction, we're creating new carbon-hydrogen bonds. I don't see any new carbon-hydrogen bonds. Where's my new carbon-hydrogen bond? All right, remember, our hydrogens are implied. So let's start filling these in here. How many hydrogens are there on the end? We got 3. Same thing on this end. Okay, what about my carbon right here? How many hydrogens? 2. And what about that carbonyl carbon? How many hydrogens?
0.
It's got none, right? It's already got its 4 bonds. If we go over here, okay, our ends also have 3 hydrogens. This one still has its 2 hydrogens. But now what was formerly my carbonyl carbon here, how many hydrogens do I have on there? Now I do have 1, okay? So we said that our reduction reactions are all about creating new carbon-hydrogen bonds. Our hydrogens are implied, so we might not explicitly draw it out here. But here is my new carbon-hydrogen bond that's been created in this reduction reaction. Okay? And again, to be clear, there would have been no difference if I had used sodium borohydride. I would have gotten the same thing. Okay? All right, one more thing that I want to say before we move on here about these reagents. Let's call these our correct. Reagents here. I've been kind of lazy in drawing them out. So for example, when we had our Grignard reaction, I just put this MgBr here. That is truthfully what's very important in our reaction. You need both of those to figure out what your product is. But if I was being really good, I would have made note of the fact that you always do this with a second step that they call an acidic workup, where you follow that up with some weak acid. And it has no difference in terms of how you would draw your products for this reaction. Just when you look in your textbook and when you look on your homework, you're going to see this second step with this hydronium ion. You're like, oh crap, what is that doing? That's just part of the reaction mixture when we do a Grignard reaction. All right? Likewise, our reducing agents. Take this same acetone here, this same ketone, and hit it with one of our reducing agents. I guess just to be clear, what's our product of this first one? Again, our reducing agent, the sodium borohydride. As we said, that would reduce a ketone to an alcohol here. All right, again, if I'm doing my true correct list of reagents here, I'm not just going to write the sodium borohydride, but I'm also going to note that in a second step, we also have that acidic workup. All right, and so why do we need that second step? Well, it turns out that the hydrogen on my alcohol that I get in my product actually comes from that acid, not from my other reagent. Okay, so it doesn't impact the way that we've been predicting our products up until this point, but I just want to make note of what you're going to see on your homework and what you're going to see on your textbook when you look up these two reaction categories. All right, so let's just say our correct reagents, they will include that that hydronium ion step. All right. Cool. So oxidation reduction, not too terribly bad. We got one more reaction of alcohol to cover, and these are what are called dehydration reactions. In a dehydration reaction, you have the loss of H2O. That's where that name comes from. All right, these dehydration reactions, we've already kind of covered a very similar one. It's called dehydration in this case because we're starting with an alcohol, but these are elimination reactions. So, the bad news is we're going to talk about elimination reactions again. All right, this is what we learned last unit when we were talking about alkyl halides and how they can undergo elimination reactions to produce alkenes. In this case, we're going to talk about converting alcohols to alkenes. Okay, so the bad news is this wasn't the most fun thing in the world that we had to do before. The good news is that there's really nothing new that we're going to add on here. It's the exact same kind of process of trying to predict what your alkene products are. All right, so let's just stack two examples next to one another here. I lied. Let's first lay out just the most simple one that we can have. Okay. We take isopropanol here. You dehydrate your alcohols by treating them with this very strong acid, sulfuric acid, and heat. Right? So you boil the crap out of your alcohol in the presence of this ridiculously strong acid, and you get a dehydration reaction or an elimination reaction that creates an alkene. All right, and this is called a dehydration reaction because we're losing water. Well, I see that I'm getting rid of an OH. Where's that other hydrogen come from? The neighboring carbon, right? This one over here also is going to lose a hydrogen. So you see in these dehydration reactions, you get an alkene and water. Now, water as an inorganic product is not really what we're concerned about. What we care about is that alkene product. All right, but this was a very simple alcohol here. There was only one alkene product that I could have. All right, let's just remind ourselves for these alkene products, we had these two important factors that we were going to consider. How substituted that alkene was, and the stereochemistry of that alkene. All right, so let's do two examples here. We're going to take this alcohol, we're going to dehydrate it with our concentrated sulfuric acid and heat. Okay, I will tell you that there are two alkene products that you can get, and I want you to try to find those two alkenes and tell me which one is the major product and which one is the minor product in this reaction. So again, good news is, same game we played before. Bad news, it really wasn't the most fun game in the world. All right? So I need to get rid of this OH group, but I also need to get rid of a hydrogen on the neighboring carbon. And in this case, I got these two neighbors here. So my product is going to depend on which one of these I choose to remove my hydrogen from. If I take it off of the green one, I will get my carbon-carbon double bond formed on the left here. If I take it off of that red one, I'm going to get my carbon-carbon bond formed on the right. Okay, so I got these two different alkenes as my dehydration product. Let me get rid of my little color dots here so we can look at these a little bit easier. All right, and just like before, I can ask you to draw the products, but I could also ask you what is going to be the major product and what are going to be the minor products of this reaction. All right, so which one of these is going to be the major product? The one on the left or the one on the right? The right, right? So this one we would call a monosubstituted alkene because that carbon on that double bond is only bound to one neighbor. This one would be a tri-substituted because I got 1, 2, 3. So here's the major product. This one's the minor product. All right, but now let's do one more example. So again, we're going to take this alcohol here and we're going to dehydrate it. But I'm going to tell you now there are 3 potential products. All right, everybody take a second and see if you can't give me these 3 potential products of this dehydration reaction. Cool. All right, I know I need to get rid of this OH group. And I need to get rid of a hydrogen on the neighboring carbon. But again, I got two neighbors that I could choose from. And I'm going to get a different alkene depending on which one of these I choose. So if I get rid of a hydrogen on the red carbon, that would give me that alkene. If I get rid of the hydrogen on the green carbon, just make more room. That'll give me that alkene. All right, but then we said that there were 3 potential products. We got 2 of them here. What's my third one going to be? Yeah, so the cis isomer, right? So the other stereoisomer of this thing here. This is the trans stereoisomer. Because these are not identical groups on either one of these carbons, I can swap these here. And by that I mean swap the hydrogen and that methyl group, and that would give me my cis product. All right, so again, we got these 2 considerations here. We have our substitution of our alkene product, but also that stereochemistry of our alkene product. Kind of the worst case scenario here. All right, and then so then which one of these, if we go A, B, or C, which one's going to be my minor product because of our substitution argument? A, so this one's the least substituted. So boom, that's my minor product there, okay? But now which one's going to be my other minor product because of the stereochemistry argument? C, right? We don't want those methyl groups to be on the same side. They want to be on opposite sides of that alkene. So, whoops, not minor. So my major product will be B here. Okay? Now, again, this was the exact same game that we would have played if I had instead given you an alkyl halide, put a chlorine here, and said we got an elimination reaction. Right? You would have given me the exact same products with the exact same major and minor distribution here. Okay? So same type of reaction, another elimination reaction. So we have those same considerations. All right, but again, now we're going to be starting with an alcohol, and we call it a dehydration reaction since it's water that's being kicked off. Cool. So unfortunately, that stuff's not going anywhere. We're going to have to practice that again for this unit. Good news is you'll be well practiced by the time we get to that final exam, right? Cool. All right, we'll start in our next chapter, next class period.